Good day to all of you. So, today we are going to start a new lesson in research methodology. It's a very beautiful day here today in Canada. It's slightly chilly, so I decided to put up a jacket as well in case if you notice. So, that being said, so today we are going to discuss further into correlations. Now, in the previous week, we discussed about some of the basics of correlation. Now, today we are going to discuss further about correlations to have a better understanding about different types of correlation and why correlations are required, and from thereby how exactly we are going to utilize them in our research. Now, let me share my screen so that you can have a glimpse of what exactly we are going to discuss today. All right. Now, Pearson correlation, Spearman correlation, Point-Biserial correlation. So these are all correlations, and then I'll be talking about another type of test called chi-square test statistic as well. So these are all tests that one could do in order to identify associations between variables. Now, these are the learning outcomes of this lecture. The first one is to understand hypothesis testing using Spearman and Pearson correlations. And then we'll be understanding the key differences between Pearson, Spearman, and Point-Biserial correlations. So then demonstrating basic understanding of chi-square test is the next bit that you would want to go through here. So now let's first talk about correlations. Now, we know that correlation is a statistical technique one would use to measure or rather describe the relationship between two variables, let's say academic performance and the number of hours a person has studied. So, academic performance is one variable, the number of hours a person has studied is another variable. So, we just try to find the degree of association between these two variables to pretty much see whether there's a relationship between these two variables. So, in correlations, we discuss this as well. So we usually consider only two variables. And here I have given actually number of hours studies and the student grade. So why exactly do we use correlations? Now, I went through Graviter and Volno, the statistics book for behavioral sciences, the 8th edition. It's a bit older edition. I used that in my undergraduate studies as well. So this is something that you can go through as well. You can purchase this book. It's an excellent book to understand a step-by-step statistical, like how to do statistical analysis. And in addition to that, now being a lecturer in the field of psychology, I'm not the smartest person when it comes to statistics. So what I do is I actually go through my books to understand more about how to do, when to do, and what stuff I need to do to understand more about research and also what to do with the data that I have. So why do we use correlations in that sense? So one is correlations can be used to make predictions. Now, if we have two variables, we can use it to understand the performance of a particular person. For example, think like this. Now, here I have given SAT and GPA. Now, SAT is the Scholastic Aptitude Test. Scholastic Aptitude Test is a test students in America would do prior to the entrance of the university. Now, international students also can do this test. And if you are an international student, if you perform well on SAT, they will give you a good scholarship. Now, how do they know that you would have a better uh, chance of succeeding? And therefore, why would they actually give you a scholarship? See, here's the reason. They have tested SAT for a long period of time and they have observed the SAT scores of individuals with their GPAs, maybe later in their academic life, or maybe they can give it to individuals who are in the second year, third year, and fourth year of the campus, and then once they do the SAT, they can simply put a correlation of the SAT marks and their GPAs. So if you didn't get what I said just now, so what they do is they give the SAT for the students who are going to the university, And at the same time, they can stay for a few years and observe their GPAs and then correlate the scores. If there's a positive trend, then you know, yes, if the SAT is up, GPA is up as well. So that you know, if someone has a better SAT score, they will probably have a better score for their GPAs. And for you to understand this further, what you can do is you can select a group of students, let's say juniors in the university in their third year or seniors in their fourth year. You can actually give them SAT and then correlate their fourth year GPA and also the SAT as well, cumulative GPA and the SAT. They are also, if you observe a positive trend, very similar to what you observed with university entrance and also uh, their scores after 2 years. So if both of these generate positive correlations, then you know SAT a good measure. That's a good measure that could give you some understanding about the grade point average of a student. So this is how you make a prediction. So we know if someone scores well on SAT, there's a good chance that they will uh, have a better capacity to succeed in the university, something like that. So that's how you make a prediction. But this is not the only way of making a prediction. Of course, there are a lot of other validity theories that you have to consider for this. But for the time being, this is what correlations can get you. Okay, this is one of the things the correlations can get you. And then the next one is validity. Now validity means the degree to which the scale measures what it claims to measure. Now, let's say you develop a new scale. You want to do a study to see whether this scale would actually correlate with other similar scales, and if not, scales that corresponds with different constructs that are closely related to what your scale measures. So think you have generated the scale or you have developed a scale that measures self-esteem. Now, your new self-esteem scale, if it is given to 100 individuals, and if you give Rosenberg's self-esteem scale also for 100 individuals, since they both measure self-efficacy, self-esteem, it should both correlate well with each other. If there's a negative correlation or if there are low correlations, what this means is that your scale has some issues. Because both the scales measure the same thing, then there is no way that there is going to be a negative correlation here. So there needs to be a positive correlation. And if someone is self-esteem, if someone's self-esteem is positive, their level of efficacy and then their confidence and these things tend to be positive as well. Optimism. So you can use your scale along with these scales for a group of individuals and see whether there will be correlations. Then those correlations will strengthen the validity of your scale. So then testing validity is another thing that correlations can offer you. And very similar to that, reliability. Reliability is the consistency of a measure. Now, for example, your newly built self-esteem scale, you want to make sure whether it is stable across time. So you give the self-esteem scale today, and then you give the same self-esteem scale for the same individuals maybe a month later. So the scores have to be roughly equal. The whatever the overall score the person is going to get, it has to be more or less similar, because I don't think self-esteem of a person get crushed over a small period of time. Maybe for one person it could be true, but you don't see it across a random sample of, let's say, 100 people. So then the scores of the two instances once again have to be roughly consistent, and if that is the case, then there will be a positive correlation. So then you know your scale is reliable. So that is another thing correlations can offer. And lastly, theory verification. Now, I have been researching self-efficacy, and very recently with a group of students in undergraduate classes, I did a very small data collection about uh, it's about a research where we try to understand the relationship between self-efficacy and mental well-being. Now, the students got the data, and then we plot them on a scatter plot, and then we ran a correlation, and the correlation is a positive correlation. So yes, if someone believes in themselves, which is what self-efficacy is all about, they should have a better mental well-being. So I'm not saying self-efficacy is the sole predictor of someone's mental well-being, but then again, there needs to be a positive correlation because that is what the theory suggests. So if your data also shows that, then this is once again a great way to verify that theory as well. The applicability of those theories in the local context is something that you can demonstrate through these kind of correlations. Now, these are benefits of correlations, all right? Now, let's discuss about Pearson correlation. Now, we have some understanding about correlations. In the previous week, we have discussed about correlations, okay? So I am explaining these correlations as a liberal arts researcher, okay? I am not explaining this as a statistician. Statisticians may have far more in-depth understanding about these correlations, how it works, and even the math associated with that. So today I am going to show you the mathematics associated in these kind of analysis, because especially in our field, in at least in our country, in our field, most of the psychologists are not too savvy when it comes to manually doing these kind of statistical analysis. And also, one of the common things they might probably say is that, look, you can use SPSS, use Excel, you don't need to learn these things manually. So I am not going to teach you how to do these things manually, but I want to show you the exact process so that you would have a better understanding about what is Pearson correlation, what is Spearman correlation, how these things change. So these kind of things. And there are some other little things that you have to understand. For example, what is covariability, what is variability, what is sum of products, what is sum of squares. So these are descriptive things that is required for you to understand how to do a t-test later, how to do an ANOVA later. So right now you are learning the very basics of research methods, but after some time you need to learn advanced statistics as well. So maybe when you go for your master's or for your PhD, you will learn. So without struggling over there, it will be very good if you can understand what exactly these things are and then go ahead and get things done. Okay. So let's try to understand Pearson correlation. Okay. Now, Pearson correlation is one of the most commonly used types of correlations. And we also call this Pearson product moment correlation. Now, Pearson correlation helps you to measure the degree of correlation. So it generates a correlation coefficient, right, denoted by simple r. So for example, simple r equal to 0.80 means it's a strong positive correlation. And at the same time, the fact that it has a positive or a negative value, that indication indicates the direction of the correlation. Positive means x increases, y increases. Negative means x increases, y decreases. So it gives you an understanding about the degree and also the direction. So previously in our lecture, we discussed about correlations. You can check the previous video. Now, let's try to understand more about how you derive at this Pearson correlation coefficient. Okay, now Pearson correlation is identified by simple letter R. Now, this R, here's what you do. It is equivalent to the degree to which x and y vary together. Okay, x and y vary together divided by the degree to which x and y vary separately. Okay. Now, here I have mentioned if the correlation is perfect, every change in x is accompanied by a similar change in y. For example, let's say there's a student who studies 9 hours and he has a score. And there's a student who studies 10 hours and he has a score as well. And then 11 hours, a score. So there is a very clear variation. There's a very clear change. So when x changes, the y changes in a particular manner as well, in a very perfect correlation. Now, this x and y always varying together is what we call covariability. Because in a correlation, there's a linear, it's a linear relationship, right? So in this linear relationship, whatever the change that happens in x, there is always a corresponding change on y as well. So number of hours, the grade. So when this changes, this also changes. There is no way that this is going to change, but this doesn't, because this is a linear relationship. So That is exactly how a positive correlation would work. In positive correlations, if there's no correlation, yes, it might not change. But in a positive correlation, when this changes, this has to change. So x and y both together changing is what we call the covariability. Okay. And then if you just consider x just one variable, you will see some variation in that variable as well. So that is the variability of a single variable. So we have our formula here, that is x and y varying together divided by x and y varying separately. Now, how are we going to find the degree to which x and y varying together? There's a formula for that. Degree to which x and y vary separately, there's a formula for that. And we are going to learn that. And once you learn it, you will notice correlations are much more simpler than you would think. Okay. Now, how are we going to calculate this Pearson correlation? So you need two things for this. One is the sum of products of deviations. We call it the SP. So the sum of products is the first thing that you want to get. That's the degree to which x and y vary together. And then you have another one called sum of squares denoted by SS. So this helps you to identify the variability within a particular variable. So sum of squares of x will indicate the variability of x variable. Sum of squares of y will indicate the variability of the y variable. So now, first, let's try to identify the formula for sum of squares. Sum of squares is denoted by sigma now of x minus mean x times y minus mean y. So I'll show you how exactly you need to do this. And then uh, you can calculate sum of products as well. So sum of products is calculated by sigma xy minus sigma x times sigma y divided by n. And then finally you have your correlation coefficient. Now in the previous one, I haven't included the square root, but the real formula is sum of products divided by sum of squares of x times sum of squares of y and the square root of that, okay? So this is the final formula. Now, this is what the Gravity and Volno book gives as the formula. Now, let's say how exactly we are going to do this. Now, we have two formulas. So, okay, now sum of products is this. We already have this. You can write this on your book and do it with me. And then here you have the correlation, the formula, sum of products over sum of squares x times sum of squares y and the square root. Now, let's think of a particular scenario. Now here we have scores of the two variables. These are raw scores. Here you have your x variable and here you have your y variable. Now let's think of a sample study, maybe number of times the person has watched a movie and the satisfaction. Now the first person has not watched any movies, maybe in the last week, and he has a satisfaction score of 2. This person has a score of 10, sorry, frequency of 10 and has a score of 6. This one, frequency is 4, satisfaction is 2. 8, 4, 8, 6. Now, x variable indicates the frequency, y variable indicates satisfaction. Now, here we have only 4 individuals, sorry, 5 individuals. So, not a larger sample. So, let's try to identify the correlation here. So, what's the calculation that you want to do? First, what you have to do is you have to calculate the average of these numbers. So for example, if you get the first variable, which is x, 0 plus 10 plus 4 plus 8 plus 8. So we have to first do this calculation. So 10 plus 4 is 14. 14 plus 8 is 22. 22 plus 8 is 30. So 30 divided by 5, the answer is 6. That's the average. So then mx is the mean x, that is equivalent to a 6. Then you do the calculation for y, okay? 2 plus 6 is 8, 8 plus 2 is 10, 10 plus 4 is 14, 14 plus 6 is 20. So 20 divided by 5, your mean y is 4. Now the first step is completed. Now start a new column, name it as deviations. And now we are going to do the next step, which is x minus mx. Now my mx is 6. Now subtract this value from each one of these x values. So for example, 0 minus 6 is minus 6. 10 minus 6 is plus 4. 4 minus 6 is minus 2. 8 minus 6 is plus 2, and 8 minus 6 is plus 2. Now, there's a way that you are going to check whether your calculation is correct here. So if your x minus mx values are correct, when you add all these numbers, the highlighted numbers up, the final answer will always be 0. See, minus 6 plus 4 minus 2 again minus 4, plus 2 plus 2, so minus 4 plus 4 is equivalent to 0. Now you can do the same thing to y as well. So y minus my, again 2 minus 4 is minus 2, 6 minus 4 is plus 2, 2 minus 4 is minus 2, 4 minus 4 is 0, 6 minus 4 is plus 2. You calculate it once again, it's equivalent to 0. Now your second step is also done. Now, to find the variability in each variable, you have to have your squared deviations. This will help you to find your sum of squares. So that is x minus mx squared. Now, x minus mx is here. Squared means you have to multiply this by the same value. 6 times 6 is 36. 4 times 4 is 16. 2 times 2 is 4. 2 times 2 is 4. And the same goes to the next one as well. And you add these guys up. 36 and 16, 46, 52, 4, 56, and then 4, 60, another 4, 64. So sum of squares of x is 64. Okay. So that is a very important component, because now we have our SSX. That is something now we have. Now we have to find SSY, sum of squares for y. So y minus my squared. So y minus my is here. You square these values. So everything is 4. You add all these guys up. Your answer is 16. Now you have sum of squares for x and sum of squares for y. Now we need to have our sum of products. So sum of products would be x minus mx times y minus my. X minus mx is here times y minus my. So negative 6 into negative 2 is plus 12. 4 into 2, 8. 2 into 2 negatives both, so plus 4. Again, 2 into 0 is 0. 2 into 2 is 4. And you add these guys up, your number is going to be 28. So sum of products is going to be 28. Now, here we have our Pearson correlation formula. So Pearson correlation formula is sum of products divided by sum of squares times sum of squares x times sum of squares y, and you take the square root. So sum of products is 28. So 28 divided by the square root of 64 times 16. So that would be 28 divided by 32, and you would have a resulting Pearson correlation of 0.875. Okay. Now, this is the Pearson correlation. Now, this is when you have only 5 data. So if you have 30 pieces of data, you can do this you can repeat this same thing for a few other rows as well. So 25 more rows. So you would have some understanding. Now, we don't need to do these things manually, but the reason why we do this is so that you would have some understanding about what is covariability of x and y, and what is variability of x and variability of y. So for you to give that understanding only, I actually did this, and also for you to have some understanding about how the scores for these formulas are derived. Okay. And as you see here, both of these are continuous variables. Okay. That's the Pearson correlation. Now I plotted this on this graph in Excel. So last time we discussed how to plot a graph on Excel. Now this is the scatter plot, and this is the relationship for the same data that we discussed. So the correlation coefficient was 0.875, and here's the data. Now this data is described, the association of this data is demonstrated by this particular vertical line. Now this resulting graph I actually use on Excel. I use the Correl function, so Correl, and then the resulting correlation coefficient is R equal to 0.875, and then I squared this value, so that you can find correlation coefficient of determination. which is 0.76, that is 76%. So 76% of the time, the variability of x variable is explained by your y variable or vice versa. Now, this is a very strong correlation. It's a very strong correlation, but still, we have to test this for its accuracy. In now, if we consider this for a study, and if we come up with a hypothesis, we have to test this data for a hypothesis as well. Now, although this is a very strong correlation, since we have a very small sample, there's a chance that this might not be statistically significant. So that is something that we need to find. So let's discuss more about how exactly we are going to do this. It's a very strong correlation, but I need to check whether it is statistically significant or not. So what I'm going to do is I'm going to do hypothesis testing. Now, this is for a non-directional hypothesis test. So non-directional means I'm not saying whether it's going to be a positive or a negative correlation. I'm just saying there's going to be a significant correlation, statistically significant correlation. Okay. So now the null hypothesis of a correlational study or analysis rather would say that there is no correlation or the correlation is closer to zero. So if the correlation is closer to 1 or not equal to 0, then that's your alternative hypothesis. Okay. So in pure statistical notations, as per the book of Graviter and Volno, you can write your hypothesis like this. So here we have used the Greek letter rho. So null hypothesis is rho equal to 0, which means there is no correlation. And rho not equivalent to 0, that means there is a real correlation. Okay. So that is exactly how we are going to do this. So now a sample correlation closer to 0 provides supports for your null hypothesis. So if the correlation, the resulting correlation is closer to 0, you would have to accept your null hypothesis. But if it is so far away from 0, which means closer to 1, there's a good chance your correlation is statistically significant. Now for that, there is a bit of a process for us to do the hypothesis testing. Now, here's what you need to do. First, you have to identify your sample size. Now, I know our sample size is 5. And alpha is 0.05. Now, whenever we do hypothesis testing, we have to specify our alpha based on a specific confidence interval. So I have a confidence interval of 95%, which means the resulting alpha is 0.05. Now, what this alpha is, it's a bit of a tricky thing to explain it in very simple terms. So I have actually, written it here as well. So in very simple terms, alpha is the probability of making wrong decisions. If I make a wrong decision, it has to be less than 0.05%, which means out of 100 times, if I make a mistake, it has to be less than 5 times. So the lesser this value, if it is less than 0.05, I am always safe, which means my study is significant. So that is why I'm specifying this alpha 0.05. So in usually psychological research, we always specify it as 0.05. But I read somewhere that in fields like engineering, where you do, this engine making and stuff like that, you go for a 0.01 because you can't have this kind of this much of chance of error. Okay. So sample is n is equal to 5, alpha is 0.05 with a confidence interval of 95%. Now, then you have to get your correlations table. Now, in the Gravity and Wall notebook, you would find this in your appendix. But if you don't have it, you can get this from Google. And it first wants you to come up with degrees of freedom. Degrees of freedom is n minus 2. Now, here, the degrees of freedom for correlations are the total number of score pairs minus 2. So now we have 5 score pairs. No, so our n is 5. N minus 2 is 3. So n minus 2 is 3 right here. And our level of significance for the two-tailed is 0.05. So 3 and 0.05 So our resulting value should be greater than 0.878. That's the cutoff point. If your study is statistically significant, the resulting correlation has to fall beyond 0.878. But now our correlation has a value of 0.875. It is very close to being statistically significant, but there is a little bit of an issue here. Why? Because we are falling short of 3 points. Why? Because we have a very low sample size. But let's say we have a sample of 20, or our degrees of freedom is 20 rather. If that's the case, see, 20 for the same 0.05, the significance would be 0.423. So if our critical cutoff point is 0.423 for a larger sample of 20 or degrees of freedom of 20, then probably this statistic is statistically significant. But since we have a very low sample, unfortunately, this is not statistically significant. Now, statistical significance in SPSS is denoted by these two ways. When you run a correlation analysis, it will generate a table, and in this table, it will show that with 1 star, if it is significant at 0.01 alpha, 2 tails, and then 2 stars to 0.05, 2 tails. So it will look something like this. Now here we have a table, education, age, IQ, and then income, education, age. Once again, we have here 3 other variables, and here they have given the correlation. So some of these correlations are significant, denoted by stars, and some of these are not very significant. So these are things that you would be able to notice uh, uh, when you do these kind of analysis, especially when you do on SPSS. So this is something that you have to notice. Okay, right. So I have given actually another sample as well. This is once again a sample that I did with my students. So you can just get a screenshot of this one, and then we have done most of the analysis. Just the final bit is remaining for you to complete. So once you complete this, you can find the correlation coefficient of this particular set of scores as well. So once again, frequency of gameplay and satisfaction. So these are the two variables. So you can go ahead and calculate this. Now, that is Spearman correlation. Now, very similar to that is Pearson correlation. Pearson correlation. Now, very similar to Pearson correlation, you have Spearman correlation as well. Now, this Spearman correlation is a very good alternative for Pearson correlation. One, when normality is not available, and also when both the variables are measured at ordinal level. Now, if one of the variables is still at ordinal level, you can go ahead and do a Spearman correlation, and instead of a Pearson. And also, if your normality is violated, you can do a Spearman correlation. Now, another thing that you would have to understand here is, now in Pearson correlation, it was about linear data, which means the data has a relationship, but it demonstrates the relationship if there is a linear relationship. So it can only show linear relationships. It can understand linear relationships better. But some of the relationships are not always linear. It will take a non-linear approach. So now, for example, consider this. Now here we have amount of practice and level of performance. Now, amount of study and grade might have a linear relationship, but amount of practice and level of performance might not. Let's say you are a cricketer. You go for a academy and you start to practice, and suddenly you notice a peak in your performance. But after a particular amount, your performance kind of plateaus. Now here your performance, still there's a slight increment, but after some time, it would plateau. Now, this is not a usual linear relationship. This is a non-linear relationship, because when x increases, y increases, and y still continues to increase, but not in the same intensity, because when y increases, the corresponding when x increases, the corresponding increment in y is not equivalent to the increment in x. So when first x increases, y keeps on increasing, but after some time, the x keeps on increasing at its usual pace, but y kind of slows down. So there's a general positive trend, but it is not linear. So what this means is there is some positive trend, there is some consistency in the overall, that positive trend, but then again, it's not linear. So Spearman correlation is when a researcher wants to measure the consistency of a relationship between x and y. So more than the linear relationship, here you can actually go ahead and observe relationships in non-linear relationships. Now, once again, I have demonstrated how to do a manual calculation here. Now, this is your ordinal data. Now, unlike the Pearson, here you have to rank your data. Sometimes we call this Pearson rank correlation, because now here you have almost a perfect monotonic relationship. So you have your x data and you have your y data. So 3, 4, 8, 10, 13, this is your x variable, and your y variable is 12, 10, 11, 9, 3. So just by looking at this, we know this is a negative correlation, okay? Because x variable at its lowest, y is at its highest, and then this goes up, this seems to go down. But now you got to rank these. Now this is our data. Now let's rank all of these data. So 3 is the lowest, so I'm going to rank it as 1. 4 is the next one, so I'm going to rank it as 2. Then 8, I'm going to rank it as 3. 10 is 4, 13 is 5. Now I have ranked them. Okay, no? But however, in our second variable, 12, that is 5 when we rank it, because from the lowest to the highest, that is the highest. So I'm going to rank it as 5. 10, however, is not the second highest, but the third highest. So I'm going to write it as the third highest of that variable, because the fourth highest is 11. And then 9 and 1. So instead of using this original raw data, we actually use this x and y ranked data. And using this ranked data, we go ahead and do our analysis. So the first step is to find sigma xy. So 5 times 1 is 5, 2 times 3 is 6, 3 times 4 is 12, 4 times 2 is 8, 5 times 1 is 5, and you get the sum of all of this. So together sigma xy is 36. That's your first step. Okay, no, so you have raw data, you don't use the raw data because you need to get ranked data. The formula is more or less similar to Pearson correlation, but the only difference is you rank them. You rank them. Once you rank it, then you can go ahead and do your analysis. Now, first, very similar to Pearson correlation, you have to have your sum of products, that is the covariability of x and y, and then you need to have sum of squares for x and sum of squares for y to find the variability of each variable. So sum of squares for x, there's a formula sigma x squared minus sigma x squared over n, and then the same goes for the sum of squares for y as well. And then sum of products would be sigma xy minus sigma x times sigma y over n. Now, here I have shown you how to do these formulas. Once again, you don't need to manually do it. I'm just showing it to you so that you have that understanding, like, okay, this is exactly what is happening here. So here, these are the answers. So sum of products is negative 9 divided by square root of 10 times 10. So the answer is negative 0.9. Now that's the correlation coefficient. Okay, now that is Spearman correlation. And now Spearman correlation also, you can do the hypothesis testing using the same tables that we utilized to do the hypothesis testing for the previous sum. Now we have some understanding about Pearson, Spearman. Pearson is for continuous data. Spearman is for non-normal data, non-linear data, and also when you have ordinal data. Now we have point-biserial correlation. Point-Biserial correlation is another type of correlation that you do when you have one continuous variable and one categorical variable, but dichotomous options. Dichotomous options means your variable has only two options, for example, two categories like men and women. So it's a categorical variable. Now, Pearson has continuous variables. Spearman has ordinal variables. This has categorical variables. For example, gender. Now, I'm not going to talk about how many genders are here. That's a different argument altogether. But let's forget about gender. Just think about a variable where it's only male and female. Male and female. So then you have two categories within that variable, whatever the variable that it is. And then college graduated, not college graduated. Once again, two categories for that variable. Firstborn child versus later born child. Success versus failure on a particular task, older than 30, younger than 30. Likewise, now these are dichotomous variables. So you have more than two categories, then we call them polytomous variables. So now this is a dichotomous variable and a continuous variable. So you can calculate once again a point-biserial calculation, by a point-biserial correlation for that kind of data. Now, I'm not going to show you how to do that since we are doing a beginner level class, but I just need to introduce it, and then the resulting correlation coefficient can be further interpreted through R squared, which is coefficient of determination, okay? Okay, now we have completed our correlations. So the next one that I want to discuss is chi-square test statistic. Chi-square is something that we use in advanced statistics, like even structural equation modeling as well. To interpret a model, we use chi-square statistic along with a few others as well. But now here we are going to just learn about the chi-square statistic, and basically to see what exactly is chi-square statistic is and why we use chi-square statistic. So chi-square test for goodness of fit uses sample data to test hypothesis about the shape or proportions of a population distribution. Now, let's say like this. There are medical students, and I would go and tell men prefers medicine more than women. Now, we have one variable that is men and women, and then we have their frequencies. I am saying men prefer medicine more than women. You are saying, no, it's not like that. There is no such preference. It's 50-50. Now, I need to know whether the preference that I'm saying is actually there or not. So I go and talk to a bunch of medical students, and I identify their genders, whether they are male or female. And somehow I find that, let's say I had a chat with 100 people. In my chat, 75 is men, the remaining 25 is women. Now, there's a difference. It's not 50-50. It seems like one group is preferred more compared to the other, or one group has more drive compared to the other. So there is something going on. So I am going to check whether this preference is significant or not compared to the usual 50-50. Now for that, I can do a chi-square. Now let's see how exactly we are going to do this. So I'm going to take you through an example Graviter and Volno has put on their book. So a psychologist examining art appreciation selected an abstract painting that had no obvious top or bottom. So hangers were placed on the painting so that it could be hung with any of the four sides of the top. Sorry, at the top. So now there's a picture. There is no particular side for it. So you can hang it up on the wall in any particular side that you think is correct. So the painting was shown to a group of 50 people, and each person was asked to hang it up on the wall in whatever the orientation they feel like putting it up. So 18 people went with the correct choice, with the top up, the original, this thing. And then 17 people did the bottom up. A few did the left side up and a few did the right side up as well. Now the question is, for us to test whether there is actually a preference for people for these, because this is not equal, right? 18 prefers this, 17 prefers this, but for the other two, it's 7 and 8. If there is no such preference, then each one should have equal number of people, more or less. And we don't see that. We see a clear inclination to certain choices. So is it just by chance, or is there is some sort of preference? So that is what we are going to check through a chi-square test statistic. So the first step that we are going to do is we need to come up with our hypothesis and select our alpha level. So the hypothesis can be stated as follows. So this is your null hypothesis, H0. In the general population, there is no preference. No preference means each choice is equally selected. So we are allocating 25% for each because we have four choices out of 100%. If we have four choices in a society where there is no specific preference, each one should have 25%, right? So 25% for the first choice, 25% for the second, 25% for the third, and then the same for the fourth. But if there is some preference, one or more of the orientations will be preferred by others. Now, that is our alternative hypothesis, which is what we are interested in demonstrating and accepting. So for that, I am going to use the alpha of 0.05. Okay. Now, once we do that, our step 2 is to locate the critical point or the cutoff region. Now, here, unlike Pearson correlation, where degrees of freedom is n minus 2, here it is actually C minus 1. So C means how many categories you have. Here we have 4 categories, remember. So C minus 1 is 3. Now, C minus 1 is 3, and under the alpha of 0.05, so my cutoff point is 7.815. If the resulting value of this analysis is more than 7.815, I am going to accept it as statistically significant. Okay. So for DF0, for DF's degrees of freedom equals 3 and alpha 0.05, the table of critical value for chi-square indicates that the critical, this x squared, this is not really I don't remember the exact Greek name for this letter, but anyways, this is how you demonstrate the chi-square. In it should has a value of 7.815. So your resulting value has to be more than that. Okay, now let's check that out. But before we do that, we have two other calculations to do. There's two things that you need to know before you do this. First, you have to calculate your expected frequencies, and then you have to have your observed frequencies. Okay, so let's first calculate the expected frequencies. These are our expected frequencies. Okay, now we are expecting to have no preference in the normal society. Okay, but we have observed some preference. So what we want to do first is to get some numbers for our expectations. So there's a formula for that. So proportion times n. Now our proportion is 25%, right? So 25% means if you write it as a fraction, that is 1/4 of the total n. The total n is 50. So 1/4 of the total n of 50 is 12.5, right? You understand that, right? So you have a sample that is 50, and for one category you are expecting 25%. So which means 1/4 of 50, which is equal to 12.5. That is your expected frequency. Now you need to have your observed frequency as well, but you are expecting 12.5, but when you actually calculated and collected data, not calculated, when you collected data, you actually observed 18 here, 17 here, 7 and 8 here. So nothing is at the expected level. So for that, we can do the chi-square test statistics. So this is the formula: sigma times observed frequencies minus expected frequency squared divided by expected frequency. So for example, first one is 18. 18 minus 12.5 squared over 12.5 plus uh yeah, sorry. Yeah, here's how it should go. So this is the first bit. The after plus it would be the second one. So this is the first, what do you call, the observed frequency, that is 18. 18 minus 12.5 is the expected frequency. Now you have to square that and then divide it by, again, the expected frequency, which is 12.5. Now that is the first one, and then you have to do the same for the second one, which is what I have given here, and then again for the third one, and again for the last one. So 17 minus 7 minus 8 minus, and you do the calculation, and your resulting value is going to be 8.08. Now you have to state your decision. Now 8.08 is falling beyond 7.815, and as a result H0 is rejected, and the researcher may conclude that the four orientations are not equally like to be preferred. Instead, there are significant differences among the four orientations, with some selected more often than others, less often than would be expected by chance. It's like, let's say, forget about this hanger side and all of that. Think about car brands in Sri Lanka. People always go for Toyota. I'm not saying always, but most of the time, because there's a second-hand market, and then you can easily, it's a it's an asset that you can very, it's easier to liquidate, right? You can quickly sell it compared to a Nissan car. So then, as a result, and due to what Sri Lankans believe, most Sri Lankans will go for a Toyota compared to Nissan. But if you consider another brand like Honda, maybe some people would prefer Honda more than Nissan, but not up to the level of a Toyota. But maybe Nissan, when compared to Daihatsu, might have similar preference. So Daihatsu, Nissan, Honda, Toyota. We interview, let's say, 100 people and look for their vehicles. Let's say a sizable portion likes, let's say, uh, 35 likes Toyota, 30 likes Honda. Now we have 65 over there. Another 20 prefers Nissan, 85, and 15 prefers Daihatsu. Now you can do the same calculation that we did to identify whether there is actually a statistically significant preference for certain brands, or whether it is, just purely by chance. Now this is what you do in a chi-square test. Okay. Now uh, this is pretty much what I wanted to tell on the first lecture of today's class, where you have to have some understanding about Pearson Spearman correlations, understand difference between Pearson, Spearman, and Point-Biserial correlations, and also have some understanding about chi-square test. So I would encourage all of you to download the Gravity and Wall book, or purchase it, and then actually go through this content to have a better understanding about how to do this step by step. So if you don't like to have that, you can go through a lot of other freely available material, both on different academic websites, university websites, and there's plenty of YouTube channels as well. And then you can go through them and have a better understanding. But here the intention is to give more of an overview as to what exactly is happening. So once you have this overview, it will be easier for you to go ahead and continue your research work. So at this point, you are not expected to do a full-blown research. Since this is your first year, the basic understanding is to try as much as possible. So as long as you do that, you are in safe hands, and that's the intention of this particular session as well. So if you have any questions, just let me know. But for the time being, this is the one that I wanted to cover. And very similar to this, I will see you with the similar video in future. So thank you very much.